we've looked at matrices for linear transformations that represent nice geometric operations in R2, but what about R3? So the thing about R3 is, right, if you have, so my usual way of drawing R3 has been a box, although when I draw this box, you have to understand that R3, the vector space R3 really extends in all directions. The box is just sort of to indicate how many dimensions there are. The thing about this is, so if the origin is here, there are sort of copies of R2, or subspaces that look like R2 in each face. So so if this is the x-axis here, and then the y-axis is going that way, and the z-axis is going up, the xy plane looks like R2. The xz plane looks like R2. And it's a little hard to draw here, but back here, the zy plane looks like R2. So if we want to do a geometric operation in R3, if it's aligned well with the coordinate axes, we can just do that operation for the coordinate plane that affects that operation and leave the extra direction alone, right? The thing about rotation, reflection, and shear is that it doesn't, none of these operations involve all three directions at once. They only involve either one or two directions, and so we can sort of pretend they're two-dimensional, but then put them in the bigger three-dimensional context. So let me show you what I mean. As an example, let's rotate an angle theta about the x-axis. Okay. Well, if you rotate about the x-axis doesn't change, right? So any vector that's pointing purely in the x direction won't change, and that means that we're going to end up with just a 1 in our upper left-hand corner. In fact, the x rotating about the x-axis doesn't change the first standard basis vector, so that means that our first column is going to be this first standard basis vector, right? This transformation doesn't change the first standard basis vector. The only thing it changes is the y and z directions. So what you can do is sort of partition this matrix. Right? Here's the input y, the output, and the input z, the output y, the output z. We can concentrate on the part of this matrix that just tells us how the y and z directions are changing. So if we rotate about the y-axis, then let's see. So I guess we have to decide for an orientation on this, and I'll use the right-hand orientation. So take your right hand, put your thumb in the direction of the positive x-axis, your fingers point in the direction of positive turning, so the y-axis is sort of playing the role of our horizontal axis, even though there's more than one horizontal axis. So that means that the y position gets the cosine, and then, right, the yz gets the minus sine. Okay, and then sine theta and cosine theta. And we get zeros here. So you can see that when we think of this rotation as just affecting this back face, the green one here, we see that rotation about the x-axis in R3, it really only affects the x and y, or the y and the z direction. It leaves the x direction alone, and so the matrix reflects that, right? This matrix is going to leave the x direction alone and only rotate the y and the z into each other. So in general, right, for these rotations in R3, rotations with the coordinate axis as the axis of rotation, you're going to get either this if you're rotating about the x-axis. If you rotate about the y-axis, then your y position is going to stay the same. And let's see, if you rotate about the y-axis, then z is actually playing the role of the horizontal axis. So the zz position gets cosine, and this is going to be minus sine. Sine here, and cosine there. So it's a little strange that you get the minus sign in a different place, but that's because of the orientation of the rotation. So have to be careful. And then if we rotate about the z-axis, then it's the z direction that isn't changing, and the x and y direction get our usual rotation matrix like this. Okay. For reflection, it works pretty much how you would expect. So if we reflect across the, across the xy plane, this is really reflection in the z direction. And so you get the identity matrix, except you get a -1 on the direction that you're reflecting. Right? So reflection in the y direction is going to look like this. And this is reflection. Reflection in the y direction is reflection across the xz plane. And then the last one, reflection in the z direction, or sorry, in the x direction, this is across, reflection across the yz plane. And this is just -1, 1, 1 down the diagonal. And as usual, any entry that I don't write is a 0. So I guess this just leaves shearing. So let's shear let's say the x-axis in the z direction by some factor c. So remember how this worked in R2. The axis that you're shearing, that tells you the column. So we're shearing the x-axis, so we're going to have a non-zero entry in our first column. And the direction that you're shearing tells you the row. And so this C is going to go in the first column, third row, so there. And then down the diagonal, shearing always has a 1. Right? So here's a shear of the x-axis in the z direction. Just for another example, if we wanted to shear the y-axis in the x direction by, I don't know, by c. So the y-axis, that means we're going to use the second column. In the x direction, that means first row, so we're going to get a c right there. And 1's down the diagonal as usual. All right, so for our 3 geometric operations, rotations, reflections, and shears, we can do it in R3 just as well as we can do it in R2. Let's look at an example. Let's find a matrix for the linear transformation in R3 that rotates about the y-axis by 3 pi over 4, and then shears the z-axis in the y direction by 3. So this operation happens first, so that matrix needs to go on the left. This operation happens second, so that matrix has to go, I'm sorry, I had that backwards. The rotation happens first, so it goes on the right. The shear happens second, so that goes on the left. The shear is easier to write down, so let's do that one. So we're shearing the z-axis, so shears always have 1's down the diagonal. So we're shearing in the z-axis, so that's third column. We're shearing in the y direction, so that's second row. And we're shearing by 3, so we need a 3 right here. 0's everywhere else. Okay, so now for the rotation. We're rotating about the y-axis. That means the second column and second row aren't going to change from the identity, so it's the same second column and second row as in the identity. Now we just need to decide where do all our sines and cosines go. So if you think about x, y, z like this, if you rotate about the y-axis, right, you have to use the right-hand rule to decide what orientation things go in. So thumb points along the y-axis, your fingers curl from the z towards the x-axis. So the z-axis is playing the role of the horizontal axis. So get cosine theta here and minus sine theta here. That means there's a sine theta here and minus, sorry, cosine theta there. Okay. So theta is 3 pi over 4. So cosine of 3 pi over 4 is root 2 over 2. Minus root 2 over 2, sorry. Sine of 3 pi over 4 is root 2 over 2. And then minus root 2 over 2. Minus root 2 over 2. And now we can multiply these things. So of course it's pretty big and nasty just because we're in 3 by 3 here, but that's okay. There are so many zeros in the matrix on the left that the matrix product isn't going to be too bad. So first column, sweeping down the rows, we get minus root 2 over 2. This is the one where we, no, this 0 hits that 1. So we get minus 3 root 2 over 2, and then minus root 2 over 2. Second column, because it only has a 1 in the middle, it's just going to pick out this second column here, so 0, 1, 0. And then for third column, we're going to get root 2 over 2, 1, no, minus 3 root 2 over 2, and minus root 2 over 2. Okay, so there we go. There's the matrix that performs this linear operation in R3.